Okay, thank you very much, Renee. And first of all, thank you, Mihal, for putting together this wonderful conference and for having me here. So it's actually the second time I've been to Warsaw, and the first time was right before the lockdown. So I've come full circle, kind of, but it's a very wonderful place to be. Okay, so today I will talk about a work that has been done together with Tobias Schätz in Freiburg for the most part. It concerns the interactions of ions and mostly rubidium atoms in composite optical traps. So the outline of the talk will be like this. You can forget, because the previous speakers have done just such a great job of motivating what is going on and why we want to do this. So I will just mostly skip to the results, where I show you what we can see in terms of interactions of barium ions embedded into a gas of rubidium cloud. And then I will discuss what performance and limitations we can see, and also discuss the prospects of this particular approach. But then I would like to conclude with some kind of speculative part, where I will present some new ideas about how to extend these techniques that we have developed for ions and atoms to something new. Okay, so first of all, that is the promised slide that I can skip. So we want to be free of radio frequencies, because we want to avoid micromotion-induced heating, obviously. And the applications of optical traps for ions are manifold, but I will focus on ultracold ion-neutral interactions in this talk. So then this is a slide that I have not stolen from the previous speakers, just very, a very famous theme. So I mean, I will not bother you with explaining this all over again, but essentially the story is it started up more than 10 years ago with initial experiments, and then this field of research has expanded a lot, and there are now experiments all over the world, and so this is in no chronological order or whatsoever, so it's purely random, and I apologize if I forgot anyone. Yeah, but again, just to the point, the challenge that the field has mostly been facing is due to rf-induced micromotion. And this imposes a limit on the collisional energies that we can have, so that if you want to do these experiments in presence of radio frequencies, then there are a few options that we have. And those options are, well, the ones that are successful right now is to go to very low reduced masses, which means use heavy ions and light atoms. And there is wonderful work from René Geretsma's group, who showed features that strongly deviate from the classical Langevin behavior. So that worked out very well. And then in our team, with Tobias Schätz, we have implemented also a heavy ion, barium plus and lithium, and then we have seen Feschbach resonances, so you have seen talks about this by Tom. But then there are also other approaches to do it, so essentially this was touched upon in the last talk. So if you use the fact that you can excite Rydberg atoms, then you can essentially make that interaction happens at a distance where the micromotion is not so bad. So that is like one way to do it, and then there are also very nice experiments in the heart of the quantum land, Stuttgart, so where they have essentially made use, very, very clever use of single excitation of rubidium to Rydberg states to make studies of very, well, essentially the same physics, but on different time scales. Okay, so I will just go right ahead and tell you about the experiment we did in the bichromatic trap. So first of all, why do we need a bichromatic trap? The answer is easy. We need to trap essentially atoms and ions in the same spot, which means we need optical traps that will be attractive for both species. The way we do optical trapping for barium is by using a 532 nanometer laser, which is red detuned for the barium S2P transition. But as it so happens, it is blue detuned for rubidium. So that means that the sample would be anti-trapped. So to cancel that out, we need an additional light that does the opposite but stronger. So we have an additional light at 1064 nanometers, which is red detuned, and we have to kind of crank it up high enough so that it overcomes the repulsion of the blue detuned beam, plus some surplus to provide for the optical trapping potential. And that means that the potential look vastly different. So in barium, they add up constructively. And the depth for that we aim for is on the order of millikelvin. So that is not fundamentally limited, but it is mainly due to the fact that we just initialize our atoms at Doppler temperature. We don't have to do that. In principle, we could go lower, but because of the way we do the overlap, as soon as the ions see the atoms, they are heated up anyway. And that is up until the point where we can switch off the RF, so it doesn't help us too much to go lower, but there are different schemes where we can make use of this. So this explains why the trap for the barium has to be much deeper. And then for the rubidium, we need to be ultra cold, so we aim for temperatures that are on the order of 10 microkelvin, which means we need like 300 microkelvins worth of trap depth. So we achieve this by overlapping these two beams, and we focus them down to a waist radius of 4 micrometers, and they are matched at the center. And this now allows us to prepare the ions in the pile trap. So you can see the RF electrodes here and the DC electrodes. The DC electrodes are always on for us, so the DC confinement axially is always present, whereas the RF electrodes are only on for loading, preparation, and detection afterwards. Fluorescence detection. During the actual experiment in the bichromatic trap, we switch that off. So what does the experiment look like? What are the signatures we want to observe, and what is the observable? So for us, we have the optical trap, and the optical trap can be used to overlap the ions in the atoms in the same spot, but they can also be used to measure the temperature at the same time, as you have heard in Tom's talk yesterday. So what does temperature, how does it look if we have a higher or lower temperature? So what we measure is kind of trapping probability of an ion as a function of trap depths. So we kind of sample the Boltzmann distribution, and then we can defer from it what was the temperature. And the only thing that you need to know about this is essentially that the colder the ions are, the higher the trapping probability is at any given trap depth. So the signature that we're looking for is that the trapping probabilities go up. And yeah, you have also seen this in the talk yesterday. Essentially, you start off with a Doppler-cold ion, and then we immerse it into 500 rubidium atoms trapped in this bichromatic trap at a temperature of roughly 30 microkelvin. And the interaction time we aim for is 0.5 milliseconds for technical reasons. You can ask me later why, if you want. And in this regime, we expect on average something like 1 Langevin collision, 0.7 to be precise. So with this now, we perform the experiment, and we see a clear signature that the trapping probability went up everywhere, which means that we have cooled. And since we started at the Doppler temperature roughly, this clearly is sub-Doppler cooling, and this is nice because it kind of took out 1/3 of the entire kinetic energy in a single collision, which is nice. And it's the first time that rubidium that was pre-cooled to millikelvin temperatures has been cooled to sub-Doppler temperatures, whereas all previous experiments have shown that for this particular combination in a hybrid trap where the RF is there, you would expect heating, and you see that. Okay, and then the limitations, I will discuss this in the next slide in a bit more detail, but essentially we concluded that the main limitation to the interaction times that we can have and also the cooling efficiency that we can achieve is due to Poynting stability, and that is because the beams, the way the experiment was built, are counter-propagating, and then the differential shifts matter a lot. And this then leads to density fluctuations, and that means that our experiment averages over many, many iterations, of which some don't even see atoms. And then there is also photoassisted loss from N3-body recombination and other loss mechanisms that limit us to this narrow region of space in, well, parameter space where we can perform the experiment. So nonetheless, we have seen the cooling by 100 microkelvin. So this is the plot now that shows the cooling. This is a calculation, by the way. So this is the expected cooling. The blue line is what we have measured. And now on the x-axis, you see something that's called trap probability. So that is just a binary number that tells you, are the lasers fully aligned or not? So if they are not aligned, that means that the barium ions see no atoms. And then why did we do this analysis? Well, we observed in an experiment in independent measurements when we only load atoms and see what is their position, and we see that they are only at the position of the ions actually in 30% of the cases. So 2 out of 3 shots, there is actually no alignment. So the analysis that we have performed before is a conservative analysis that averages over everything, and it assumes that there is always overlap, but that is not the case. And then if you can take this into account, then the picture changes entirely. So here we can see 0 Langevin collisions, 1, 2, and so on and so on. And then what we see that if we assume conservatively that the overlap is there all the time, like we did in the paper, then you would expect that you can clearly distinguish between, say, 1 collision, 2 collisions, maybe even 3 collisions within our experimental uncertainty. However, if you go to the regime where we probably were experimentally at 0.3 overlap, then you can see that all of them actually bunch up in a very narrow region of space, which means that the actual temperature in the shots where the atoms and ions were aligned should have been much, much lower, and in fact could be as low as the atom temperature, 30 microkelvin. But it also tells us that the method we use is not resolved enough to distinguish these effects. Right? With this, now we see that the limitations that we see right now are technical, so it's the fluctuations of overlap between the ODTs. But that, in a sense, is good news because there are very well established ways to deal with that. So you can just stabilize the beam pointing, which we have not done before. And more importantly, we can just send the beams from the same side so that we cancel out common fluctuations, common mode fluctuations. So I think with this we can improve quite significantly, but the more general problem is that for rubidium barium, the S-wave energy actually is pretty low. It's 50 nanokelvin, and that doesn't go away just because you're in an optical trap. So you need either much colder atoms, which means you need to cool way further down than 30 microkelvin, so you need to go to a BC, or you need a different mixture like barium and lithium. And if you go to BC, then you have very high densities, typically in the order of 10 to the 15 per centimeter cubed. And there you run into 3-body recombinations, which are very well known. And they actually even don't go away for lithium-6, which is fermionic, as we have seen yesterday also. So the way to deal with it would be to think what is the next iteration of a composite optical trap that takes care of this. And one way to do it would be to overlap the trap with a standing wave of the 532 nanometer laser, which would then essentially, on the left you see the effective potential calculated for barium, and on the right for rubidium. Then you would see that at the lambda half spacing, you would see the minima for barium, and it repels at these positions rubidium, so you would see no rubidium here, and the trap would then be like a very thin sheet type trap, lattice trap for rubidium. So by separating the wave packages, essentially you can go into a regime where you can tune the elastic to inelastic collision ratio while still probing a ultracold gas. So I'm almost out of time, so we'll hurry up. Recently I started working with neutral ultracold molecules with bosonic sodium, potassium in the ground state in Hannover, in the group of Silke Osbeckhaus. And then I realized that there are many parallels actually between the two fields. And since this field also has seen a very rapid development recently with the achievement of degenerate Fermi gases, there is maybe a way of even combining ions with molecules nowadays, because in some way the methods that I have talked about are very compatible. So if you look at what you need in terms of what the setup needs to look like, dimensions, compensation, isolation, what are the optical transitions and the timescale for experiments, they are quite compatible. So it should be possible to do these experiments. And the overlap protocol is actually identical. So NAK is a molecule with a large permanent dipole moment of 2.8 dBi, so it's very highly polarizable. And you can calculate the C4 coefficient for this, and it's 30 times the C4 coefficient of rubidium. And the R star is now the characteristic length is 2.2 micrometers in this case. So in the vicinity of the ions, the NAK will experience a field and will get strongly polarized, as you can see in the sketch here. And then there will be a rich kind of interference, not interference, but competition between interactions on different time scales. So there is the interaction that we know, 1 over R4, that's charge-induced dipole. That is kind of sort of long range on the scale of 2.2 micrometers. But if the ions, with the molecules are pulled in, then this becomes not the dominant interaction. Instead, you have the charged and permanent dipole, the scales 1 over R squared. But then at the same time, there is the dipole-dipole repulsion from the molecules. And that actually can be used to stabilize the collision. So by pulling them in, they are polarized, aligned with respect to each other. And this should give rise actually to repulsion. And then if you look at the details, so I'm out of time, I will skip over it in a hurry. But essentially, yeah, if you go to close range, then Olivier has calculated for me, so thank you very much, on for this system that there are several reactive channels open, but they would take place essentially up to 25 AU. You would be safe from this. But long before that, the field is exceptionally high. So it would be polarized way before that happens. And then if you do the calculation for something like 340 molecules, which is something that one could do in a degenerate molecular gas, then you actually would expect some local minima in the effective potential, which then could be used to study new ion molecule clusters, polarized type physics, and things that are related to the talks of the previous speakers, actually. So sorry for overstepping a bit. So I will just thank you very much for your attention.
Okay, Stefan gets to ask one quick question. Make it good. Make it count.
Thank you very much for the interesting talk. So can you say a bit more about the photo-assisted losses that you have been alluding to, and how bad are they?
Yes, so they are pretty bad, especially from the 532 nanometer beam. So that is very well known. So Johannes has studied it in detail in Ulm. So this is the reason why we can only do it for half a millisecond. So if we do it any longer, then we run into problems with that. But of course, if you can go to denser atoms, say BSE, then the time scales changed, and half a millisecond is a long time, essentially.
Okay, so thanks, Leon.